Start with questions. Does anybody have questions from the homework or otherwise? Okay, sure. Okay, 31 says find the exact value without using a calculator. So the tricky part here on 31 is that the angle measure you're given isn't in degrees, but rather in radians. What I would recommend here is just converting this angle measure to degrees, since it'll be easier at that point to use our 30, 60, 90 and 45, 45, 90 triangles. So to convert from radians to degrees, I multiply by 180 over pi. That was our conversion factor. So the pi's cancel out. 6 goes into 180 30 times. So I'm left with this is 30 degrees. So if I draw my triangle now, what I have is a 30, 60, 90 triangle. I remember that the ratio of side lengths, the short side is x, the medium side is x root 3, and the long side is 2x. So sine of pi over 6 is going to be the same thing as sine 30, which is opposite over hypotenuse. So I have x over 2x, which all reduces down to just 1 over 2. Does that feel okay, Nathan? Okay. Boyd. 33. Okay. So that's cosecant of pi over 3. I'm going to start the same way and convert this into degrees, so it's a little bit more comfortable. So that's going to be 60 degrees. So again, now that I have that, I can draw my 30, 60, 90 triangle. So I have cosecant of pi over 3. And I know that's the same thing as cosecant of 60. And cosecant was hypotenuse over opposite. I can reduce the x's. And then I would want to rationalize that denominator. So I'll multiply the top and bottom by root 3. To give me 2 root 3 over 3. Alternatively, if you wanted to, you could also write this as like 1 over sine 60. But now you're talking about having like a fraction inside of a fraction, which seems like maybe not the easiest way to go. But if you wanted to, you could have gone and done that. You would have ended up still at the same place if you wanted. But I probably would have passed on that. Well, I did pass on that. It seemed less confusing to just use my definition of cosecant of hypotenuse over opposite rather than 1 over sine. Although not incorrect to do it that way, just for the record. Who else? Yeah, Lucas. 39. Okay, it says if A is 38 degrees and B is 10 to solve for C. So just kind of recopy that triangle. And it says A is 38 degrees, B is 10, and we're looking for C. Maybe I'll just call it C. So I'm going to look relative to the angle that I know. So relative to that angle, the 10 is adjacent, and the C is hypotenuse. So the trig function I want to use should contain the adjacent and hypotenuse. So I'm going to use cosine. Which I know is adjacent over hypotenuse. And now it's just algebra time, so I'll multiply both sides by C. And then divide both sides by cosine 38. And then it's just calculator time from there. What do you have to be careful about your calculator? You'd have to make sure it's in degrees to type that in, right? I think there's been problems before this where you had to reset it to radians to do like cosine of 1.7 radians or something. So you have to be careful there that you're moving your mode back and forth appropriately. And Lucas, I'm going to save the button pushing for you guys. Is that cool? Okay. Yeah, that was 39 or something, I think you said. Okay. Any more takers? All righty. So today we're going to do section 2.4. And we're really going to do something special here today in section 2.4. So if you remember last time in section 2.3, we came up with this new method of drawing angles, right? We called that the standard position for an angle. And this new method of drawing an angle allowed us to draw angles of any size between negative infinity all the way to positive infinity, which created a whole new world outside of geometry, right? Where we're stuck with angles between 0 and 180. We can now draw an angle of any size, no matter what. Does everybody remember kind of how to do that? So if I want the standard position angle for, 451 degrees, so we start by drawing the XY axis. The vertex of our angle is always locked at the origin. And one arm of our angle is on the positive x-axis. And then to draw the other arm, we rotate starting at that initial side on the positive x-axis, which way do we rotate? Counterclockwise, to our left, right? I should say to our left, correct. It's confusing if I want to say to your left, right? It's a dumb way to say it, Mr. Kulik. Okay, so how do I know how far to go? Well, how far is one quadrant on your xy axis? How many degrees has that got to be?
90.
Each quadrant is 90 degrees, right? So here to here is 90, then 180, 270, 360, 450, and then like one more degree is just barely creeped onto the second quadrant. Is everybody okay there? Cool. Okay.
So you have to draw that circle, right? In order to...
That would be part of drawing the 451 degree angle, as I would expect to see that rotation mark there. Mm-hmm. Mm-hmm. So the next thing we did after this was then we defined So the next thing we're going to do now, we have this new way of representing angles, right? And we have talked about how sine, cosine, tangent operate on the acute angles from a right triangle. We're going to take these two ideas, stuff them together to come up with a new definition for sine, cosine, and tangent. Okay? So, let's say that we have some standard position angle, and let's say that we've picked some point P on the terminal side of our angle. So here's my angle theta. On that angle, or on the terminal side of that angle, I've just picked some point. I'm calling that point P. That point P has coordinate x, y. So what can I do with this? If I look at this angle, what does it almost look like? Almost looks like a triangle, right? If I drop a perpendicular from that point P back down to the x-axis, in fact, I've created a right triangle. Everybody's okay with that idea? So, according to the picture I've drawn, what should this side length be in my right triangle? That thing in yellow. What should the side length there be? How do I plot a point using its coordinates? What's that? Olivia, go ahead. It's like a pre-algebra question. It's not. I'm not trying to be tricky here. So what direction do you go on the x? Okay, but you go left or right. So in this case, how far to get to point P would have we gone to the right? x, whatever that x coordinate point P is, right? Everybody's okay with that? And how about to get to this, the green side then would be y, right? We've gone x over and then y up, and that should get me to point P. Everybody agree with that? So nothing tricky there. The other side of this triangle, I'm going to refer to as R. And just using the Pythagorean theorem, R should be the square root of x squared plus y squared. Is everybody okay there? So if I do sine theta here, if I use my geometry definition, sine theta is opposite over hypotenuse. In the picture I've drawn, what is opposite? Y. And what is hypotenuse? I'm just going to call it R so it's not so busy. Everybody's okay with that? Let's pause here and look at what we've really done, because this is actually really significant, what we've just done. We've now defined sine in terms of the coordinate on some point on the terminal side of a standard position angle. Right? We can now find the value for sine without using the acute angle from a right triangle. All I need is a coordinate on that terminal side of my standard position angle. Huh. All right then. Likewise, we can do the same thing with cosine. What will cosine be? X over R, thank you. And tangent will be y over x. Cosecant should be R over y. Secant should be R over x. And cotangent should be x over y. So this, super important. This is a new way to define sine, cosine, and tangent using a point on the terminal side of a standard position angle. So I abbreviated TS for terminal side and SP as standard position. Those are just my made up abbreviations. They're not really standard, but I'm going to say what they are because it just was like going to be a lot of words. So many letters. Now, what I've written here probably still needs a little tiny bit of adjustment in a couple of places. These definitions all assume that the denominator of this ratio is not 0, Why don't I have to worry about that for sine and cosine? What is r really representing? Or the distance from that point to the origin. Can that distance be 0 if I'm picking a point on the terminal side? No, right? So the point on the terminal side can't be the origin. So that distance can never be 0, so I don't have to worry about r ever being 0 there. Okay. Let's do a quick little example, and then we'll continue to kind of develop this definition, because this is not going to be the final form. Okay, let's say the point -3, 4 lies on the terminal side of the standard position angle theta. Find the 6 trig ratios for theta. So I'll start by drawing myself a little picture. And I'm going to plot the point -3, 4. Everybody's okay with the picture I've drawn here? Notice for this angle, I don't know the exact angle measure. I don't even know if I'm talking about an angle like this as theta, or like an angle like that for theta, or even an angle like this for theta. It doesn't matter. All I need to evaluate sine, cosine, tangent, etc., is that point on the terminal side. I don't care which direction I spun. I don't care how many times around I spun. I don't need any of that information. Everybody's okay with that? So I'm just going to delete out all those rotation marks so that when you look at the notes it's not confusing. But I want to just point that out for a moment. Yes, sir. Standard position. Yep. I'm going to use that abbreviation pretty frequently for standard position. Okay. So the 3 things I need now, if I'm given a point on the terminal side for a standard position angle, to do my trig ratios, I need a value for x, I need a value for y, and then I need a value for r. Okay? Well, x is -3. Y is 4. R is the square root of x squared plus y squared, all square rooted. Here we have to be a little bit careful about the way you're typing things into your calculator, particularly when you're squaring negatives. So -3 times -3 is +9, right? If I type -3 squared in my calculator, why am I getting -9? Yeah, you need to put a parenthesis around the -3 before you hit the squared, or the calculator is going to follow the order of operations strictly, where the negative comes in the same place as multiplication. So it's going to do the exponent and then make it negative, following the order of operations. So please be careful there. I see that frequently, even amongst like the very good math students, make that mistake on their calculators. So I got that R is 5. Everybody cool? Okay. So sine theta is y over r. Cosine theta is x over r. Tangent theta is y over x. Cosecant theta is the reciprocal of sine. Secant theta is the reciprocal of cosine. And cotangent theta is the reciprocal of tangent. So I'm done. What do you guys think? Super easy, right? No big deal. Let's do another example. Everybody's cool with that? Okay. So what if we asked you to find the cosine of 150 degrees without your calculator? Well, I know that I should recognize immediately that 150 degrees is not a geometric angle value I can do using a right triangle, since that's an obtuse angle. So I'm going to start by drawing my standard position angle for 150. So here's my initial side. I rotate 90 degrees and then like 60 more to get to 150 degrees. Everybody's cool there? Okay. I'm going to pick some point P on the terminal side of that 150 degree angle. And then I'm going to draw my triangle. When I draw my triangle, I am always going to draw my triangle to the x-axis. If you draw it to the y-axis, you will not get the correct result. And what is this angle down here going to be? 30 degrees. How do you know that's 30 degrees? That is correct. Because that angle, along with the 150 degrees, should form a linear pair, adding to 180. Everybody's okay with that? You remember that term from geometry? Maybe, or not. A linear pair is two angles that lie on the same line. You have like one line divided into two angles. Those two angles form a linear pair. The sum of the two angles has to equal 180 degrees. That's what we have there. Okay, so if that angle's 30, oh, by the way, what we've drawn here, this guy is called a reference triangle. Just as a heads up. That's what that thing in blue, that triangle in blue that we've made there is called a reference triangle. So the other angle in my reference triangle is 60 degrees, right? Everybody's cool with that? So what I notice I have here is a 30, 60, 90 special right triangle. Any of these problems where we ask you to not use your calculator and you're not given much other than an angle measure, you're going to end up with like a 30, 60, 90 or 45, 45, 90 triangle almost every time. So I know the ratios of the side lengths in a 30, 60, 90 triangle. Instead of using the variable x for the ratios, I'm going to use the letter a. I don't want to use x here because I'm going to be talking about an x coordinate, and I don't want to like abuse that notation too badly. So the ratio of side lengths are going to be a root 3, and then 2a. Okay. So what's my value for x here going to be? What do you guys got? A square root 3. Almost. Almost. What quadrant are we working in? Yeah, we're in the second quadrant. The x-coordinates I know are all negative in quadrant 2, right? Because we've gone to the left. Everybody's cool with that? The y value is going to be a, just positive. Now, this stinks. I don't want these stupid variables rattling around inside of these coordinates. Who wants to get rid of those? We would love to, right? So here's the deal. Because I can pick that point P to be anywhere on the terminal side, I can just pick any value I want for A and just put that value in there and then be done with it. What value of A is going to be the easiest one to use that's other than 0? Can't use 0. 1. So that just becomes negative root 3, and that becomes 1. Everybody's okay there? Come on in.
Sorry to interrupt.
That's okay.
Just looking for Cusack, Aiden.
He's in the back there, Aiden.
I just have a quick question.
Sure. What's the square root of, what's negative square root 3 squared come out to be? Quick in your heads.
Wait, what?
Negative square root 3 squared.
Negative square root of 3 squared.
What?
Just negative.
3.
Just 3, right? The negatives cancel out when you square them, and the square cancels the square root. Everybody agree with me? 1 squared, real quick.
1.
So R here is 2. Okay. Michael. Nope, Matthew. Sorry.
Borrow a piece of gum.
Yeah, somebody left that stuff. It's not even mine. I don't know.
You're gonna put it back.
You can
I'll put it back when I'm done.
chew it at your own risk.
Yeah, that's super.
Could be somebody's poison gum, I don't know. Or prank gum. Maybe it's gonna turn your teeth all blue or something.
Whiskey Biz.
Top of the notch.
All right. So we've done the hard part. We found the values for x, y, and r now. All we have to do is plug those in to get the values for sine, cosine, tangent, etc. What's sine going to be?
So,
I would think about it as y over r.
Yeah, y over r.
So 1 over 2. Cosine is going to be x over r. Tangent is going to be y over x. But we don't love the way that looks. So we'll rationalize our denominator. Quick question, I got a negative sign in my fraction. Does it matter where I put that negative sign?
Yeah.
No. Right? So I'm just going to stick the negative sign out front. Okay? And then my value for cosecant is going to be 2 over 1, or just 2. My value for secant is going to be except I'm going to put the negative sign just out front and just call it negative 2 over root 3. Got to rationalize our denominators again. And then cotangent is going to be negative root 3 over 1, or I'll just call that negative root 3. Oh, but what were we really trying to do here? I didn't ask for all the ratios. I just wanted cosine of 150. So we're done way back there. I did too much. Mr. Kulik forgot the original question because it got too into talking to himself about what was going on. That's okay. Yeah, we answered it. We just did a lot more too. Okay. So, we've done quite a bit here, right? There's one little thing that we could do to kind of make this process even more streamlined. What's the place where we have, seems like we have a lot of freedom? Picking that point on the terminal side, right? Seems like you can kind of just pick that to be wherever on that terminal side. And that's true, that's fine. Let's standardize that process though. So we're going to always pick that point in a certain way that's going to in turn make this process even a little bit easier. Okay? So this is our third version now. Olivia, of course. So, here's the modification we're going to make to this process. From now on, when picking our point xy on the terminal side, that's the TS, of a standard position angle, we're going to choose that P so that it's always 1 unit from the origin. What is that really saying? That if the P is always 1 unit from the origin? Tells me that the R will always be 1. Right? If the R is the distance from P to the origin, for always picking R are always picking our point, so P is 1 unit away. R has to just be 1 every time. So what is our result then? Sine theta becomes, instead of y over r, y over 1, or just y. Cosine theta becomes, instead of x over r, just x. Tangent doesn't change because it was already y over x. Cosecant becomes 1 over y. Secant becomes 1 over x. And cotangent doesn't change. It becomes x over y. So let's think about this for a minute. If I consider all possible angles, that are 1 unit away from, or whose terminal sides, or I'm sorry, consider all possible angles. And I consider every point on all those possible angles that are 1 unit away from the origin. What's that shape going to look like? So like, this could be the terminal side 1 unit away. That might be the terminal side 1 unit away. That might be... What am I getting here? Yeah, this is a circle. Right? A circle whose radius is 1, because every point is 1 unit away from the origin. That's the center of the circle. What do we call this kind of thing? We call it a unit circle. What I wanted to do. Okay, so what we're going to do now is we've observed that when we run into one of these angles that makes a 30, 60, 90 or 45, 45, 90 special right triangle, where its reference triangle is one of these special right triangles, we can find exact values for our trig function, right? We can do this without our calculator. Everybody's okay with that? So what we're going to do now is we're going to kind of record all that information so we can create like a shorthand way of doing this. So I'm going to drop one of these guys, one of these blank ones that we're going to fill out together in the notes into OneNote. If you are in OneNote and want to follow along, I'm syncing that now, so that should be coming through here in just a few minutes. But we're going to fill this out here together, and then I'll give you guys a typed version of this as well. That'll be easier to work with. I'll dump that into OneNote here when we're finished, okay? Okay. So let's start with the easiest ones. So if I have a 0 degree angle, both the initial and terminal side are lying on the x-axis. So like that's the point on our terminal side. What's the coordinate for this point? That's 1 unit away from the origin and lies on the x-axis. You mean 1, 0. Yep. Everybody's okay there? Let's go to this 90 degree angle. So our point P would lie there, 1 unit on the y-axis, 1 unit away from the origin. The coordinate there would be very good. And if we go over here to 180, this point would be -1, 0. And if I go down to this last one at 270, that would be the point. 0, -1. Everybody's okay there? Okay. So now let's do the ones that form a 45 degree or 45, 45, 90 reference triangle when we build that. So clearly the 45 does that. And what does that reference triangle look like here? Was x, x, and x root 3, or I'm sorry, root 2. Everybody agree with that? Okay. But really we want this is our radius. We want that to equal 1. Everybody agree with that? Because what I'm really drawing in here was like that reference triangle. Everybody agree? So the hypotenuse of that needs to be equal to 1. So what does my, let's use actually, I should call those A's or something. What should my value of A there be? A times root 2 has to equal 1. What does A have to be? Well, just 1 over root 2, right? If I divide both sides by root 2. And since A is root 2, x is, or since A is 1 over root 2, x is 1 over root 2, and y is 1 over root 2. Everybody's cool with that? This spot here at 135 degrees will also make a 45, 45, 90 reference triangle. What is different about this one, though? The x-coordinate needs to be negative, but otherwise it's going to be exactly the same. Everybody's okay there? This spot down here at 225 degrees, again, also forms a 45, 45, 90 reference triangle. In quadrant 3, oh dear me, what did I just do? In quadrant 3, what's going to be different about the coordinates though? Both have to be negative. And then our last one here at 315, again, all of these form that 45, 45, 90 reference triangle. In quadrant 4, what do the coordinates have to be? X is positive, y is negative, because we're going right and then down. So x is positive, y is negative. But it's cool? Okay. Next thing we're going to do are the ones that form a 30-degree reference triangle. So again, we have a root 3, and 2a. Well, we want r to equal 1. So 1 has to be equal to 2a. What does a have to be then? 1/2, right? Everybody agree with that? So if I look at this, my x is this side. So 1/2 times root 3 is root 3 over 2. And my y is this side. So that's going to just be 1/2. Okay, so now I'm just going to go and fill things in. So I have root 3 over 2 and 1/2. In the first quadrant, everything is positive. We form a 30-degree reference triangle over here at 150. Again, the only difference here is the x-coordinate is going to be negative. We're down here at 210. Negative root 3 over 2, negative 1/2. In the third quadrant, everything is negative. And then over here in quadrant 4, the x is positive, but the y is negative. Is that okay with everybody? Notice that the coordinates, when we form the same kind of reference triangle, always are the same, right? Or I should say the reference angle is always the same. Now let's do this one where we have the 60-degree. So I'll do the same thing here. And again, r still has to be 1. So a is going to be 1/2. But this time, x is going to be the 1/2. And y is going to be the root 3 over 2. Okay. Again, in the first quadrant, everything is positive. In the second quadrant, the x is negative, but the y is positive. Oops, I forgot to write the angle measure there. 20. This is 240. In that third quadrant, everything is negative. And then in this quadrant, we are hundred. So we are x is positive, y is negative. Now, you'll notice that there's still one other set of blanks on here. What do you think these other set of blanks is? It's for the angle measure in radians. How do I convert degrees to radians? Multiply by pi over 180 was our conversion factor to go from degrees to radians. So this becomes pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and we're 7 pi over 6, 5 pi over 4, and then 4 pi over 3. Oh, this was pi. This is 3 pi over 2. And then we are 5 pi over 3. And then 7 pi over 4. And then 11 pi over 6. Dun 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 dun!
Wow.
The unit circle.
So do we have to do that for all?
No. So what we're going to be using the unit circle for is to avoid having to do that ever again. We're going to use it like a tool.
Oh, so that unit circle, like that's the same unit circle?
Yeah, it never changes. We did this once, so you can just use it, and we don't ever have to do that process ever again.
Oh, okay.
It's like, no. Not at all. Do you have to be able to use it? Yeah. Let's do an example. So before we do that, I want to point out to you what has just happened. What have we just done? So in geometry, we had sine, cosine, tangent, etc. Were defined for acute angles in a right triangle, right? Next, so in trig pre-calc, our first step then was to take sine, cosine, tangent, etc., and define them as a point, or from a point on the terminal side of a standard position angle. And in our final result, is now finally at the very end, sine, cosine, tangent, etc. are defined from points on a unit circle.
That's embarrassing.
So this was our little summary of what's happened here in the last couple of days. So at the end here, at the end of step 2, notice that cosine is x, sine is y, right? So in my unit circle, my point xy is going to be the same as cosine theta, comma, sine theta. So now, let's say I want to do sine of 120 degrees. I'm just going to go to my unit circle. I'm going to find 120 degrees. And I'm going to look at the y coordinate because sine is y. And I'm done. So it's square root 3 over 2. Wait, what? You heard me. That's over. That's what I'm saying. Let's do another. Yes, if it wasn't an angle on the unit circle, we couldn't use the unit circle to do it yet.
So that's kind of what
It should be factored, right?
it's like.
So what if I want to do tangent of negative 45 degrees? First thing I'd want to do is I want to take that negative 45 degrees and find something that's coterminal to negative 45 that lies on the unit circle. So to find a coterminal angle, how do I do that? I add or subtract 360, or if I'm in radians, 2 pi. So if I add 360 to that, that's the same thing as 315. That's a unit circle angle. So remember, tangent is y over x. So I'm going to go to my unit circle. I'm going to locate 315. And then I'm going to do y over x. Quick in your head, what's that simplify down to?
1.
Close.
-1.
Negative 1. Everybody's cool with y? Because it's the same thing on top and bottom except for the signs are different. Mr. Kulik, this unit circle thing, pretty nice, because no longer do I ever have to draw a reference triangle again, right? It's basically just we did all the work drawing the reference triangles at one time, recorded all the results, and now we're done having to do that. Yeah, that's what I'm talking about. What do you guys think? Is it okay? All right, I got one more example to show you, and then we're going to be donezos for today. All right. It says find sine theta if cosine theta is 5 over 7 and cotangent theta is negative. So the first order of business on a problem like this is I need to figure out which quadrant does theta lie. So I know that cosine is equal to 5 over 7. And cosine theta is the same as, if I'm using our step 1 definition as points on the terminal side, well, never mind. Let's use the unit circle definition. Cosine is same as x. So that tells me x is positive, right? Maybe I'll write. So that tells me I'm either in quadrant 1 or quadrant 4. Those are the places where the x coordinate is positive. Everybody's cool with that? Okay. Cotangent theta, I'm told, is negative. Cotangent theta is x over y. I know that the x is positive already. So what does that tell me about y? If x over y is negative, it tells me that y is negative. So between quadrant 1 and quadrant 4, where is y negative? It has to be quadrant 4. Well, y could be negative in quadrant 3 or 4, but the only quadrant that's in common is quadrant 4. Now, I wrote a lot of stuff down to do this. Do you need to write all this stuff down? No. You do not need to. I'm just writing it down because they're notes. And you should be able to look back and understand like how I got there. So like this is my angle here. Everybody's cool with that? All right. I'm going to construct my reference triangle now. Everybody's cool with that? Cosine was 5 over 7. So I'm going to think about this side as 5. And the hypotenuse is 7. How can I find that y side? How about the Pythagorean theorem? And remember, to simplify a radical, I'm looking for factors that are perfect squares. Stop talking, please. So that's 2 root 6. Does that all look good to you guys? Shouldn't be. There's one thing missing. Why is that negative?
Because it's on the bottom.
Yep, that's fine. If he said because it's in quadrant 4 or whatever, that's fine. Everybody's cool? Now everything's done. So all we need to do now is evaluate sine. So sine is opposite over hypotenuse. And we're done. What do you guys think? Guess what?
What?
We just finished chapter 2.
All right, that was it.
What haven't we done yet in chapter 2?
A test.
Well, what else haven't we done yet? Homework quiz.
No.
What should you expect next time?
Quiz.
Yep. So do that. I'll have a delta math assignment for you, like last time. They're all the same. They're all graded that same way. Where it's like,
Like I fundamentally like kind of know what I'm doing.
yeah, so you get like a 8 or a 9 or something. Okay, sure. So next time we'll do the homework quiz. We'll do a delta math assignment, practicing mostly this stuff from this section, which is the section that really kind of carries forward the most. We'll do a review day, or we'll do the review the next class, and we'll take a test next week.
So it's our homework quiz for class.
Yeah. So I think like Wednesday next week, it sounds like is test day. Does that sound right? Yeah. Okay.
Yeah.